Okay, my name is Frederik Ritter. Welcome to my presentation of RSESS, our open source implementation of the enumerative sphere shaping algorithm. KIT is a university in Karlsruhe in Germany, for anyone who didn't know. I'll start by talking about the internet. Works nicely. As we all know, internet data rates are constantly increasing. This means we have to use higher transmission rates, and this means we have to use newer infrastructure, but that would be expensive. So ideally, we would want to operate with higher data rates with the same infrastructure. This means we have to go closer to channel capacity. Luckily, probabilistic shaping offers 1.5 dB in gain if we move from uniform channel inputs to constant Gaussian channel inputs. And this is where we contribute a practical implementation of a probabilistic shaping algorithm coded in Rust, which you can use in research and development. But let's first take a step back and look at the general challenges for probabilistic shaping. So first of all, channel inputs, continuous channel inputs are currently not feasible. This means we will have to bite the bullet and only adjust the probabilities of our discrete channel input signals. Second, data bits are usually uniformly distributed. This means we need a shaper that converts from the uniformly distributed data symbols to, or data bits, to non-uniformly distributed channel modulation symbols. And then at the receiver, we need the D-shaper to convert back to uniformly distributed data symbols. This way, the channel only sees the shaped modulation symbols, and then we get our gain. Next, of course, our channel will never be as friendly as in the picture. We'll always have errors, so we have to use forward error correction. This was solved in 2015 by Böcherer and Schulte with probabilistic amplitude shaping. In essence, this uses the symbols, the signs of the modulation symbols to transmit parity information. For our purpose, it is especially important because this means the signs are used and we may only shape the amplitudes. So there are different algorithms that do this shaping of the amplitudes. Böcherer and Schulte themselves published constant composition distribution matching, which is a very good algorithm for long block lengths. However, it suffers from severe rate loss for very short block lengths. This is where Laroya's algorithms, they were both published in the same paper back in 1994, come in. They are good for lower block lengths, or what we'll be focusing on, enumerative sphere shaping, which is also very good for lower block lengths. It was also published in 1993 by Willems and Witz. ESS doesn't work on single bits and amplitude values, but it maps whole sequences of bits to whole sequences of amplitude values. The idea is to reach AWGN capacity by using the most energy efficient representation of our data. To this end, the used amplitude sequences in ESS have the minimal average energy. And this can be achieved by limiting the energy of the sequences used below an energy threshold. This energy threshold is then also one of the main parameters of ESS. The other two parameters are the number of amplitudes in these sequences and the modulation order, so what order of ASK we are using. So to store all these amplitude sequences efficiently, we use a trellis like this one. Each amplitude sequence is a path through this trellis, and each arrow in this trellis then represents an amplitude. We find indexes for the nodes in this trellis by taking the number of amplitudes it takes to get there, and the total energy of these amplitudes. So just as an example, if we take 2 amplitudes with a total energy of 18, we would come out at this node. By taking this indexing, we have efficiently connected the trellis nodes with the energies of the amplitude sequences, and thus by just limiting the size of the trellis, we can now limit the energy in the used sequences, and thus we can achieve this minimal average energy. The size of the what I just said. We now still need the values. The values can easily be found or are defined as the number of paths from a node to the end. So let's have an example again. We just forget the value of this node, and we can easily retrieve it by counting 1, 2, 3 paths to the end, and then we have the value to be 3. Now these values are very nicely used in the encoding and decoding algorithm. I would have really liked to talk about these algorithms, but there's simply not enough time, so you could ask me later, or you could look at the original paper from Willems and Weitz. It's very nice. Or you could look at the paper accompanying this talk, where I went into a bit more detail. But let's now go on to our implementation, RSESS. RSESS stands for RS, Rust, and ESS is, of course, ESS. It also implements the optimum ESS algorithm, published in 2022 by Chen and another Chen. It's especially good for extremely short block lengths. It implements encoding, decoding, so from amplitude sequences to bits and vice versa, and things like the amplitude distribution, the amplitude distribution and the average energy, which is good if you're doing a simulation. You have to find the average energy to do your normalization. We also publish Python bindings called PyRSESS, so you could use these from a Python script or from GNU Radio, Python blocks, or something like that. We published everything to crates.io, that's the Rust package place, PyPI, and GitHub with some examples. It's very easy to use. There's a short example using PyRSESS. You import it like a normal package. PyRSESS and RSESS use a normal object-oriented interface. So we can just create an ESS object with the 3 important parameters: maximum energy, number of amplitudes in a sequence, and the ASK modulation. Then we can define some data, and we can convert this data into an amplitude sequence using the encode method of ESS. We just get a sequence of amplitude values. Then we can play receiver and use the decode method on the received sequence, and of course we get back the normal or the bits we put in. This is, of course, a very simple example. We could do much more. For example, normal simulations will entail many, many more transmissions. So what we did is we simulated or measured the time for 10,000 encodings or decodings. We also kept the shaping rate constant so that we could compare different amplitude sequence lengths. Shaping rate is the number of bits transmitted per amplitude. And we tested all of this on an i7 from 2017. You can see the length of the amplitude sequences on the x-axis and the time for one call of the encode or decode method on the y-axis. And first thing we can notice is that ESS or PyRSESS, the Python version, is the dotted lines, is slower than the pure Rust version. I don't think this is surprising, as Python is just slower. And also, we have to always convert data rates if we're using Python. So that's not really surprising. Another thing is that encoding, the blue lines, is slower than decoding. That's just because the algorithm is more complex. In general, we can see that all execution times are below 1 millisecond, which is already pretty good, in my opinion. If we keep in mind that RSESS main advantage is its very low rate loss for short block lengths, we should know that it's usually also used for short block lengths. So if we look at block lengths below 500, we see we are even below 200 microseconds, which would be equivalent to 5,000 runs in 1 second. We also ran some memory benchmarks. Once again, PyRSESS is less efficient than RSESS. I might want to mention that these benchmarks include the base process plus the energy or the space required to store the trellis representation. PyRSESS is still very much efficient if we look at shorter block lengths as what ESS is usually used for. So we are still below 50 megabytes, so that is very much usable on any normal hardware. If we want to use extremely long block lengths, we can use a pure Rust version. It's below 40 megabytes all the way to the top of the plot. So this wouldn't be very useful if we couldn't do some real simulations with it, which of course we also did. We could even reproduce some results from literature. On the right-hand side, you can see a plot in the paper from Chen I mentioned earlier that published optimum ESS for the very short block lengths. It has SNR on the x-axis and the achievable information rate, so how much information we could theoretically achieve on the y-axis. And the most important part of these plots, why I'm showing them, is because our results are exactly the same as Chen's results. And this means that our implementation works as expected, which is very good if you're publishing a library. So I hope I could interest you in non-uniform transmission schemes to increase data rates. And I published or introduced our implementation of ESS called RSESS. It's relatively fast because it uses Rust, and the results we get using RSESS match results from literature. I hope if any of you are in this field that RSESS may be useful to you. Thank you for listening, and I think there is still time for questions, so feel free to ask.
All right. Questions? Oh man, those hands are going up left. So.
Thank you for this talk. My question is, in the last slide, you showed the achievable data rate, I guess. But how did you found it in the real implementation? How did you compute it?
In this case, I would propose you look at the paper by Chen or the paper where they got it from. I'm not sure. It's a very nice way of taking the received signals before doing the error correction. And if I remember it correctly, you kind of take the distances between what you would expect and what you receive and the log likelihood ratios. And then there's a nice formula, and you plug it in there, and then you get these achievable information rate estimates from it.
Yeah, thanks also from me. This is all the real case, right? We're just doing on one axis the amplitude shifting and...
Yes, the simulations were all real, but as it is completely, well, you can just do the same thing on the imaginary axis, then you got the QAM modulation. So these plots are showing the achievable information rate for QAM modulation.
Does that work? Because if I do maximum amplitude on I and maximum amplitude on Q, I don't get twice maximum amplitude, but I get square root of 2 because it's, or I get 2 squared because energy goes quadratically with distance, Pythagoras and stuff.
Yes.
So then...
Well, you do get different amplitude in total, but you should just be able to do both.
Okay, I mean, if you say it works independently, that's super cool, because then we just get twice the data rate, right? So
exactly, we just get twice the data rate.
Nice.
It wouldn't be this nice analogy between the amplitude and so on, but I think it should just work.
Yeah, okay, cool. Yeah. Thanks.
All right. Any more hands? Okay, in that case, thank you, Frederik. Thank you.